Okay, so thanks everyone for coming to this seminar and for the few people who are connected online. So this is one of these colloquium that we have for this series in theoretical and computational physics. Okay, so they're sort of for pedagogical kind of seminars where you can hear about the latest results in a given research field, but starting from almost the basics. So the idea is that it's supposed to be something that also students, master students in physics could follow. And today our speaker is Valerio Vitale here. And so Valerio is actually, correct me if I'm wrong, a chemical engineer by training. So he did his studies in Naples in chemical engineering. After that, he moved to the university. Actually, I can remove this. I'm not supposed to have it. To the University of Southampton. For his PhD in physics, or maybe, yeah. And after that, he moved to Cambridge, and he did a postdoc with Mike Payne and also collaboration with Arash Mustafi. And after that, he did a postdoc in London at the Imperial College with Dishner and Arash again, Arash Mustafi. So actually, he's moving to Trieste because he won a Marie Curie postdoctoral fellowship. We worked here for 2 years with a project in collaboration with Federico Becker here and me on, again, twisted bilayers and topological effects and correlation. Okay, so today, Valerio will talk about Twistronics and Moiré materials. And so thanks a lot, Valerio, for accepting the invitation, and the floor is yours.
Thanks, Antimo. Thanks for inviting me. Yeah, so as Antimo said, today talk is about Twistronic and Moiré materials. And the menus, today's menus is the following. So I'll give you a broad introduction to Twistronics, this new field, and then I'll talk about Moiré materials and the physics that can emerge from these Moiré materials. And then the talk will go to the challenges in modeling these Moiré systems, why they are challenging, and a solution that we adopted at Imperial, this multiscale approach, and then I'll show you some examples for twisted bilayer transition magnetic chalcogenides, which is a class of these Moiré materials. So introduction. Okay. So what is Twistronics? So Twistronics is this new field. It's probably 3-4 years old. And it's basically the idea of studying how the twist angle between two 2D materials can affect their electronic properties. So this is a new kind of degrees of freedom that thanks to experimentalists, we are now able to tune. And it's called the twist angle. Basically, you stack two 2D materials on top of each other, and then you apply a twist. And as you can see, basically, a pattern emerges at different angles, right? So, for example, at these particular twist angle, which is roughly 10 degrees between these two, you can see that basically you have an emergent pattern, which is called Moiré pattern. Where you have regions where the two bilayers are using AA stacking. So basically, for example, if these are two layers of graphene, these are carbon on top of carbon. And then there is these also regions where you have this AB or Bernal stacking, where carbon of the bottom layer are in the middle of the hexagon of the carbon of the top layer. And you have these alternating stacking regions, and also you have some other stacking in between. And in general, when you stack these two 2D materials and then you apply a twist, this Moiré pattern has a periodicity which is much larger than the periodicity of the crystal, of the 2D crystal. And in particular, the periodicity of the Moiré pattern goes as 1 over theta, where theta is the twist angle. Right, so small theta means large Moiré cells. The other thing is that not for all theta you can have a so-called commensurate cell. So usually these would be, most of the time, this would be quasi-crystal in a sense, because this region here would be slightly different from this region here. But at some specific angles, you'll have that you have a commensurate structure, and this structure is fully periodic in a sense. Right. So, as you can see, experimentalists have been working on this for a couple of years now, and they managed to actually produce devices with different 2D materials and different twist angles. This one in particular is for twisted bilayer graphene, which we'll talk about quite a lot. And these are STM images at vacuum, ultra vacuum, ultra cold. And you can see how the Moiré patterns generates a Moiré potential that tends to localize states near the Fermi level. So these are actual STM images of these states near the Fermi level in just the bilayer graphene. The idea is quite similar to another also recent field, which is Twistronics, where basically what you do is, instead of applying a twist, you apply a strain of one of the two materials, or you can play with two materials with different lattice constants. And you can also generate patterns like that. Right. So why it's interesting, why it's important to study this class of materials. So here is an overview of basically the scales that one can play with by tuning the twist angle. And as you can see, one can form, by tuning large twist angle, one can form quasi-crystal, as I said. Or if the angle is in this regime between 1.5 degrees and 5 degrees, let's say, we have almost, for all kinds of material, this phenomenon of band flattening, which I'll talk about more in detail later, and the correlation effects. And then if we keep on reducing the twist angle, then we have this nice domain structure that form, where the system tends to have to enlarge the regions where the binding energy is more. So this is A, B, for example, for graphene. And in between these A, B regions, there are these very fine channels where all the strain is localized. But we are mostly interested in this regime the twist the angle or between 5 and 1 degrees. And for most of the materials, this regime is where we can see correlation effects. Right, so these are the main 2D materials that have been fabricated and then they've been used for twisted bilayer materials. And we have the usual suspects here, so graphene, molybdenum disulfide, black phosphorus, boron nitride, and so on. But in theory, we could play with any 2D materials, right? So any exportable 2D materials can be a building block of this idea of twisting, stacking and twisting.
Sorry, the scales you were talking about are largely independent of the structure of the material. So that range is not sensitive to the details of the structure. Twisting structure.
You mean the range in which we see?
Which you see exactly those kind of.
Yeah. So basically, we for most of the system that we're interested in, that people have fabricated their devices like that, this range between 5 and 1 degrees is where this correlation happens. And the thing is, so the thing is that at large angle, the two layers are almost uncoupled. In this regime, there is a strong coupling, but not as strong atomic relaxation. Whereas if you go to down with the twist angle, then atomic relaxation becomes important, and we have these effects of systems that want to basically put all the strain in these kind of solitons on the structure. So you get these very large regions with one single stacking again, and very small regions with all the strain in. So the material that's been studied the most and is the prototypical Moiré system is twisted bilayer graphene. This was the first device that people managed to build at a specific angle. Was around 2018, and these are two experiments. One in 2018 and one in 2019, and the left one from a group at MIT, and the right one from a group at Barcelona. And what I'm showing here is the resistivity as a function of the filling factor and gate and temperature. And so on the x-axis is this filling factor or number of holes or electrons in the systems. And on the left is temperature. So this is basically a phase diagram, right? And what you can see is that the resistivity goes to 0 for a specific value of the filling factor. And these are actually then being demonstrated, these are actually superconducting states. Whereas between these superconducting states, there is possibly a Mott insulator or a correlated insulating state. And this was the first example of this system. You know, graphene doesn't have all of that, doesn't have, it's not a superconductor or it's a semi-metal, right? And on the right, people managed to have a more clean device where they could show that basically these superconducting states were at specific filling or fractional filling. And between these, you have these charged correlated insulated states. A second example that came a few years after that is the same group from MIT managed to build a device with a twisted trilayer graphene, and also in twisted trilayer graphene, the same thing happens basically. So you have a superconducting dome for a specific value of the filling and insulating states. Although the superconductivity or superconducting states in twisted trilayer graphene is thought to be quite different from twisted bilayer graphene. It's more robust, and it's probably a spin triplet. It's called a spin triplet superconductor. Again, the same game. People played with the twisted double bilayer graphene here, where they put two bilayer of untwisted graphene in the AB stacking, and then they twist the middle ones. And this also has superconductivity and charge insulating and correlated insulating states at different values of the angle. So graphene is basically the system that people have studied the most, but most of these states, correlated states, and the nature of the superconductivity are still not quite well understood. But the whole idea of why there are these correlated insulated states or correlated states in general is due to the fact that at least in twisted bilayer graphene at specific angles, you have this flattening of the bands. And this flattening of the bands happens, at least in twisted bilayer graphene, at an angle of 1.1 degree. And these bands become very, very flat, and flattening of bands in reciprocal space means usually very localized states in real space. So what does that mean is that kinetic energy is suppressed in these states, and this suppression of kinetic energy somehow enhances the Coulombic interaction between the states. So it's the strong Coulombic interaction between the states that generates all these correlated states. Right. So this is an overview of how the field kind of exploded after 2018, where the first device was fabricated. And here in 2011 is when this model was firstly put forward by McDonald and Istutzer. And so there was kind of excitement after the publication of this theoretical paper, and then the field kind of died out, and now after 2018 it really exploded again. But there are also, as I said, other materials that we can play with. So just bilayer graphene is not the only one that shows these correlated states. A similar physics also happens in a completely different material, which is tungsten selenide, which is not a semi-metal, but it's a superconductor, a semiconductor with a band gap of around 1-2 eV. But here as well, the phase diagram has these kind of zero resistance states that hadn't been fully defined as superconducting states. And in between these zero resistance states, there's this insulator state. In a different system, in WSC2 and WS2, so tungsten diselenide or tungsten disulfide, which have a slightly different lattice constant. This is an optical experiment where they show that basically a different value of the filling, you have all these several correlated insulated states. And some of these correlated insulated states have then been identified as generalized ligand crystals. So these are really real STM images of electron localizing in these spots and forming these charge order states. Right. So as I said, you can play with all sorts of 2D materials, and you can generate all different kinds of band structure from these materials. And this band structure and the Moiré system can inherit some of the properties of the 2D materials that you start with, but you also have all this class of emergent phenomena from the twisting. So it's really a new platform for engineering novel states of matter in 2D systems. Okay, so challenges in modeling this system. Why these systems are challenging? The main reason is, as I show you, is that if you want to study these systems, this system contains, at the regime that you want to study, at the twist angle that you want to study, contains lots of atoms, right? So if you want to study them from first principles, then you are in trouble because the Moiré cell can contain up to 10,000 atoms. And for some of these materials, you have, for graphene, not really, graphene has a quite simple electronic structure, but for other materials like transition metal metallogenites, we have quite a complex electronic structure. So you have transition metals that you have to deal with D and F orbitals, strong spin-orbit coupling, and so on. The other thing is that you really need to understand the relaxation of these systems, and this is quite important for the electronic structure, as we will see later. And you have this huge material space that basically comprises all the combination that you can do with 2D materials, from 2D materials, but which is estimated to be around a million of possible combinations. Right. So there are different ways that people have, this is a bit small, there are different ways people have try to tackle this issue of understanding the electronic structure of the systems and their atomic structure. And there are different levels of accuracy. So of course, one would like to do most of everything at the DFT level, density functional theory. But the accuracy of the DFT in terms of the band structure and the atomic structure is quite high, but the speed is low, and you can't really, have all the angles that you want, because at some point you hit the n cube issue with density functional theory, the scaling of the density functional theory, so you can't really go to very large systems. So only large twist angle. For the atomic structure, you can use molecular dynamics and elastic continuum theory. These are moderately accurate, but are quite fast in a sense, particularly elastic continuum, although the accuracy is probably not as great. For the electronic structure, again, you would go with the FT, but there are other things you could do. And in particular, these involve tight binding and continuum models. So our approach to study this system, we wanted to study a large class of Moiré materials, in particular transition metal chalcogenides. And we wanted to study different twist angles, different combinations. So we really couldn't go with the FT. So our approach was basically to combine these two different methods. And we use classical force field or molecular dynamics for the atomic structure. And then we use the ab initio type binding that we developed for the electronic structure. And I'll talk about mostly about the ab initio type binding, because the classical force fields were already there implemented in labs. So yeah, so our approach was this combination of two different approaches, different methods. So we use this classical force field to generate the atomic structures, which have been parameterized on density functional theory. And we use this ab initio type binding, which I explain what it is, that basically uses Barnier functions on the unit cell to generate the band structure of these systems at the Moiré scale. And these have also been parameterized on the DFT calculations. So basically, the bottom line is we use the FT to parameterize these systems in the unit cell, so only contain 3 or 2 or 6 atoms, depending on the systems. And then we use this parameterization on the unit cell to compute the structure and the electronic structure at the Moiré scale. Oops, this is not. Okay, so as an example, I'll show you about the transition metal chalcogenides. These are the monolayer are already quite interesting materials. They have a direct band gap. They are direct band gaps in conductors. There's this strong spin valley coupling, so you have that bands are spin polarized at the K valley, and you have opposite spin polarization at K prime. And so you have this strong light matter interaction as well with exciton binding energy of 100 MeV. And for some of the system, the one that contain tungsten, particularly, you also have this strong spin-orbit coupling. So the monolayer are already quite interesting materials. But then, as I said, you can play the game with the bilayer and the twisted bilayers. So the only, further complication of TMDs is that unlike graphene, they're not central symmetric anymore. And now you have two different classes on the way you can stack this TMD. So basically, you can start from what's here is defined as AA stacking, right? So basically, you have the transition metal of the top layer on top of the transition metal of the bottom layer, and the similar for chalcogens. And if you start from this class and then you twist, you get a specific Moiré pattern. And you can start from any of these three in this class. So basically, these three stacking, this AA, this Bernal chalcogen on metal and Bernal metal and chalcogen, they all belong to the same class. That means if I start from a bilayer stacked in this way and then I twist, I get the same Moiré pattern. But then I can also start from a different stacking, which is this 2H, where now the metal, transition metal of the top layer is on top of the chalcogen of the bottom layer, and vice versa. And you can create, so basically we have flipped the top layer before stacking, right? And you can create this Bernal stacking as well from these. And all these three belong to the same class. And if you twist, starting from any of these three, you get the same Moiré pattern, which is different from the other one. So these two are kind of topologically different. And in this class, the Bernal stacking are the one with the lowest binding energy, so they are the favorable ones. Whereas in this class is the 2H, which is the energetically most favorable stacking where the system needs to be in. Right, so you can play the same game as we played for graphene, for example, and then you generate these Moiré patterns. And these Moiré patterns will contain, if you start from AA, for example, as I'll show you, these patterns will contain regions of AA stacking and region of Bernal-like stacking, as well as other regions with, you have a continuum basically of stacking between these two. But then you can start from 2H and you get a different Moiré, whereas in this Moiré, you only get these three different stacking, right? Which are different from the one I showed you in the previous slide. So this also means that these two systems will relax in a different way because you'll have different stackings in the Moiré cell, and which have different energies. And so the relaxation will be different in these two classes. And of course, you can have, two different TMDs with different lattice constant. They already form a Moiré pattern, but then you can twist, and then you get a different Moiré. Right. So relaxation. So these are relaxation that we obtained with the classical force field, and the relaxation of the system is quite intuitive in a sense, because basically what happens is that where the stacking is AA, the two layers tend to be far apart. And where the stacking is Bernal-like, the system tends to be closer to each other, right? So this is the outer plane modulation along this diagonal of the Moiré cell. And so basically what you see is basically you have AA regions in the corner, and then you have Bernal of one kind, Bernal of another kind, with a little bump in the middle, and then AA again, right? And the system basically, the outer plane corrugation follows the stacking of the register. In plane, we have these kind of vortices, rotations around the AA regions, because the system wants to minimize these unfavorable stacking. So basically, if you are in the AA and you start rotating a little bit, you basically, what you're doing is you enlarge the Bernal kind of stacking, of reduce the AA stacking. So the system doesn't want to be in this AA. And so what happens is that you have this rotation clockwise on the top layer, for example, on the bottom layer, and counterclockwise on the other layer.
Question. Can you study this relaxation for larger angles and smaller samples, but with DFT?
Yes.
Can you check in the case that the effective model that you're using is reproducing the same kind of?
So these models are very good up to certain angles. And the things go quite badly below 1 degree, where you have these strong relaxations. So at the DFT level, and then the classical force field diverge below 1 degree. Around 1 degree is still acceptable, but in twisted bilayer transition metallic alkogenides, we don't really have to go up to 1 degree as in twisted bilayer graphene. So you can start to see these correlated states already around 4 or 5 degrees, and I'll show you why. Because it's the flattening of the bands happens already at 4 or 5 degrees. So for this regime, these classical force fields are quite good, at least for finding the minimum, the relaxations. We haven't studied phonons or things like that. Right, for the 2H, the relaxation is quite different. And as you can see, basically, you have this region where the 2H is, where the system wants to be because it's the most favorable one. And then you have these two Bernal, which have different energies, but you have this very large outer plane corrugation. And a similar thing happens in the in-plane. And basically, the atoms tend to rotate around the Bernal ones, which is the unfavorable one, to reduce the area of these Bernal. Right. So this is a way to compute the structure at the classical force field level, but as I said, that they are quite accurate in the regime that we're interested in. And then what we did was to construct a tight binding Hamiltonian, which we call ab initio, and I will explain why, from basically using the information only on unit cells. So the idea is to start from a basis of 11 orbitals or linear functions. And these are the 5 Ds on the transition metals and the 3 Ps on the chalcogens. And then we exploit some of the symmetries of the system. So basically, there are these 2 mirror symmetries. One is this in-plane mirror symmetry, and the other one is this M2. And by basically the d orbitals are all symmetric with respect to M1. So basically, you can already classify the d orbitals into even and odd with respect to this M1, but you can further classify them in terms of this M2 symmetry. And basically, you can create combination of p orbitals that are even or odd with respect to these 2 symmetries. And the reason for doing that is just that you can, separate the Hamiltonian and make it more sparse, and you already build in the symmetries of the systems in the Hamiltonian. And then we basically adopted a tight binding that goes up to third nearest neighbors. So basically, we consider the first nearest neighbors of chalcogens with metal, and then second nearest neighbors with chalcogens and metals with metals, and then third nearest neighbors again with chalcogens with metals farther away. Right? And if you do all of that and you consider symmetries, you get 40 independent parameters for the monolayer. Right? So if you want to parameterize this tight binding, you need the on-site terms and then 40 independent parameters, and then you can generate all the other parameters by symmetry. But the reason why we call this tight binding ab initio tight binding is that basically what we did is that we take a DFT band structure of the monolayer, we generate the Vanier Hamiltonian in real space, so we do a Vanierization. We generate the Vanier functions, and then we truncate the Hamiltonian in real space, and we only keep the real space Hamiltonian that is compatible with this third nearest neighbor hopping. And then we extract the parameters from this Vanier Hamiltonian. So basically, we don't do any fitting. It's not a fitting. Basically, we generate this Vanier Hamiltonian, and we just take the value of the hoppings from the Vanier Hamiltonian for the tight binding. So there is no fitting involved. The only thing that we had to introduce to make accurate band structure was this idea of interlayer interaction. The DFT level, the interlayer between bilayers is mostly of van der Waals nature. And in our tight binding model, we modeled it by using Slater-Koster rules for p orbitals on different layers. And you can show that basically these, for a definite stacking, you have these kind of universal function that you can describe the interlayer interaction quite well. So not so for definite stacking, for definite interlayer separation, right? So you can move the top layer with respect to the bottom layer, and you compute all these interlayer interaction, and they follow this PZ to PZ is able to describe this interaction quite well at a single interlayer distance. But the issue is that in our Moiré structure, we don't have a single interlayer distance, but we have different interlayer distances, so separations, as I showed in the relaxation. So basically, we had to parameterize this interaction for different interlayer distances. And so we come up with a different formula, which was stacking dependent. So it's dependent on this Z, which is basically the interlayer separation between the two layers. And you can see basically you have different, exponentially decaying curves for different interlayer separation. The other thing that also was we had to introduce was this P to D interaction, which was particularly useful to describe the states near gamma, which without this interaction, we have a quite bad description of these states, so we had to parameterize these as well. And this is basically the result of our fitting. So things are quite good for P interactions, P2P interactions. They're reasonable for P2D interactions. So basically these are Vanier hoppings compared to Slater-Coster that we had generated. And as you can see, basically if we don't include these P to D interactions, we completely miss the energy at the gamma, for the gamma bands. Right, so last two ingredients for the tight binding model were the rotation of the orbitals, of course, of the top layer compared to the bottom layer. We had to rotate the basis, and the inclusion of spin orbit coupling, which is in our case is a simple on-site term. It doesn't carry any momentum. So if you put everything together, then you get a tight binding code, that generates this structure compared to the FT. So basically these are valence band structure of different transition metallic chalcogenides twisted bilayers at 5 degrees. Green is tight binding and orange is DFT. And as you can see, the descriptor is not perfect, especially the bandwidth is quite off, but you get all the symmetries of the bands right. You can improve, as we have done later in a different work, you can improve the description by going to 4th, 5th, and 6th neighbors, and there the agreement becomes much better. But we were interested mostly in the, looking at how the band structure would evolve with the twist angle, but where the flat band would form and what kind of flat bands would form. So before looking at these, I just want to mention two things. The first thing is that you have these different stacking in your systems. And what happens is when you have a monolayer compared to the bilayer is basically near the Fermi layer, near the gap. What happens is that the gamma states go higher in energy. And so you go from a direct band gap semiconductor to an indirect band gap semiconductor. So this is the main difference between, and this, it's true for all stacking and all systems. For some systems, though, like tungsten selenide, it's very sensitive to the choice of your exchange correlation functional and the structure, and you can get that basically gamma states and K states are. So just want to mention that because these, which bands is on top, which states is on top, then will affect which are the nature of the flat band in the Moiré system. And these bands have different contributions. So basically, gamma valley have PZ and DZ square, as you can imagine. That's why it was important to introduce this in the tight binding. Whereas K valley states have high projection on D orbitals in the metal, in particular dxy and dxy squared minus y squared. Right. So what happens is the following: when you twist the material, you have these two bands forming at the top of the valence band. So these are Moiré bands, and these bands in most of the system are on top of the valence manifold. And these bands come from gamma valley. So I have a high projectability on PZ and the DZ square orbitals of your systems. But you can also have these other situation where it's completely different. Now your valence band maximums are K. These bands come from K Valley. They also tend to flatten, but they have large contribution on d orbitals now. And things get quite more challenging if you have to introduce relaxation. Because if you don't introduce relaxation, you have this spurious band structure for twisted bilayer. In this case is, I think, molybdenum disulfide. And as you can see, if you don't relax the structure, but you keep the two layers flat, what happens is that you have a band gap opening at K, and if you plot the wave functions at gamma of this band, it forms this very localized triangular lattice. But if you do relax the systems, then the band at K closes and you have this linear dispersion. And if you plot the wave functions at gamma, then it has more this hexagonal emergent lattice. So, we didn't start with any of these two lattices to start with, but then the Moiré patterns generate these states. Right, so this is just an overview of what happens if you twist the angle. And as I said, you start with these two bands that touch K, and that gives a linear dispersion. And then they become flatter and flatter. And then at 1.6 degrees, which contains up to 10,000 atoms, you have these very flat bands, particularly for molybdenum diselenide, which are very flat. And for these systems, for 1.6 degrees, you wouldn't be able to do any DFT calculations. You can play a similar game if you start instead from AA from 2H. And in this case, the 2H stacked systems have a different band structure in the top of the valence band. Now you have a single very flat band already at 2.6 degrees. So by changing the stacking, the original stacking, and then twisting, you can get a very different band structure between the two class. And then you can, play with hetero bilayers. And in hetero bilayers, as you can see, sometimes you get these K Bartley bands on top instead of gamma. So you can really have quite a range of different bands here at the Fermi level, which come from gamma or K Valley. And to conclude, I have give you an introduction to Moiré materials, why they're interesting for this idea of Moiré patterns and correlated states. Explain why Moiré materials are quite challenging from a theoretical and modeling point of view. Why you have to introduce also atomic relaxation is important. And I've shown you the case of twisted bilayer transition method with chalcogenides and the emergence of flat bands in these systems. Next, we are quite far with respect to what I've shown you here. We have already done multi-layers and better description of these K bands, as well as excitons and the absorption spectra in the system, all from this ab initio type binding model. And to conclude, these other people I should really thank, particularly Kemal, which is a PhD in our group, HP resources and fundings, and you for the attention.
Okay, so thanks a lot, Valerio, for a very nice talk. Now, of course, we are open for questions. So we'll allow people to actually unmute themselves in case they have questions online, but let's start from the questions. Right here in presence, anyone?
So are you limited with the selection of the materials? Actually, how is your space to play with it?
Yes, of course, we have only parameterized the type binding for these 4 transition metal nickel cogenites. We have a similar type binding model for graphene. These are not hard to parameterize. We have everything now in place to automatize these parameterization. But yeah, at the moment, we only have these 4 and we are parameterizing a few other. But yeah, so ideally the code would work with any system which has hexagonal symmetry. So TMDs, graphene, HPN, but you have to parameterize the type binding hoppings.
If you put in, for example, rare earths, starts to get more complicated, I think.
Well, it depends on what kind of bands you're interested in. So basically what happens is that, the bands that really contribute to the Moiré bands, let's say the states that really, from the monolayer that really contribute to the Moiré bands are those close to the Fermi level. So in theory, you could only have a very good tight binding of a single band, right? But that's quite hard to do, and you can do an empirical tight binding, but then you lose control of the meaning of these parameters. Here, everything comes from the hoppings of these orbitals. You could do an empirical tight binding where you just fit your parameters onto the FT structure. And there are some attempts, but of course, the top bands is very well reproduced, but then all the other bands are quite crap. And then you lose a bit of meaning of what then the wave functions that it generates and so on.
Please, Maria.
Thank you for the presentation. I'm interested in not say in listed bilayers, but overlay on surfaces. So typically graphene. And what I found is that it is very difficult to calculate or to predict a specific means orientation, and the energy is very, very similar. So I was wondering whether this is also the case for transition. For instance, for graphene or nickel or I found differences of the order of few millieV per hour. So what about TMD?
No, in TMD so they're not hugely different. Just like, but definitely in the hundreds of MeV.
Much more.
Yeah. So graphene on a metal.
On a metal, yeah.
But like not twisted, just the Moiré rises from the different.
Graphene on nickel monomer is the only, I think, as far as I know, the only possibility of having a perfectly functional structure.
Right.
So you may either shift or twist, as you saw in normal.
Okay. That's a good point, because exactly. So at large twist angle, what you have the two systems can be almost uncoupled, and this system like graphene on HPN or I think I've seen graphene on HPN. They also have this property of super lubricity. So basically, you can slide one on top of the other, and there is almost no energy barrier. And if you look at the phonon structure, you have these phasons, which are very flat phonons as well. So for some systems, it's true that basically you can almost slide the material on top of the other. And for MOS2, they're looking at these in the case of solid lubricators, basically. So to have lubricators that are solid instead of liquid. So I think also for TNDs, when the twist angle is large, when the twist angle is small, then you start creating these pockets of different stacking, and the two materials become more sticky in a sense. So it's harder to twist them. But a large twist angle where you basically have almost a uniform chemical environment. If I can go to the very first slide. Here, for example, basically, it's all for the system is almost, it doesn't recognize it, whether it's these or translated, right? So it's almost the same for the system to be in these kind of stacking. This is 30 degrees. Or if you translate, I can show you, if you translate, basically you get the same pattern. So for the system, it's almost indifferent. The barrier is very small. But I don't know about the graphene.
Yeah, well, if you slice it, you can reach the difference of 20 millimeter atom.
Okay.
If you twist, the difference is immense.
Right.
But we were motivated by sort of abundance of visualization found experimentally, but I think that there is no rationality because the energy is really.
Yeah.
So, if I can, I have another technical curiosity. Why would you show the comparison between high binding and DFT bands? We have angles in which, since I'm doing typical brute force DFT, I'm always in trouble with these coincidence cells that are, of course,
right.
So when you use a coincidence cell, you have to keep some tolerance because only the structure are condensed. So in this case, I was wondering how much the bands are sensitive to the, say, tolerance that you put on the coincidence supercell rather than on the parameters.
Okay, so these are the only few specific angles where you have exactly commensurate cells, and we use those angles. So here 5.08 degrees. We choose this angle because it's an exactly commensurate cell. But there is an issue where you have a system with different lattice constants, and then you twist. Then there you have to introduce some strain on or either both layers or one of the two layers to make it commensurate. And there we are yeah, exactly. We are not so optimistic on the hedge of bilayers compared to the homo bilayers, because in the homo bilayers we can have these exactly commensurate cells.
Okay, thank you.
Questions? I have one very quick one. One is a little bit long. So one is just make sure that I understand. So when you show this band structure, this is the very small movement zone, right?
Yes.
So it's used, and so what you're doing is diagonalizing this very large type of modeling, say 1,000 atoms. Okay, and so this was the first one, and the second one is in exactly this slide. So have you ever thought about kind of renormalizing the openings. Because, of course, if you truncate, and I've done it myself many times, you will never get right. By definition, you are leaving out some non-vanishing terms. And what you're showing here is that actually even the third nearest neighbor are important to get side effect. But there is a little, maybe, either renormalize some way your truncated terms. So you keep the structure, but you sort of kind of normalization method to account for the missing hierarchical openings. So you can actually go higher in normalization. So you have more states, something with more and more events. And opening should be even more volatile. I don't know if you've tried this. So, if you have a data set with a lot of empty states, I think it should be used more alive.
But then you get a worse band structure, band average band structure.
So very high energy could be variable. But the same, the digital in the end, you are really sitting on supernova region, right? But it's dealing with few MEVs for
yeah, so you're right. But the original idea was to describe both the valence and the conduction band. Right?
Okay. But just the highest valence and the lowest conduction, I guess.
Yes, the highest level. But do I have a tight binding versus the other monolayer? This is at the bilayer. But basically, you can already see that even with PZ, with DZ squared on the gamma states, we don't fully. So I know this looks very small, but on the Moiré scale, this is important.
No, absolutely.
Yeah.
But your organization ends there, almost just considering the states up to P and D, and that's it, right?
Yeah.
Those one, you start by using stuff this.
But then you have to introduce more.
Yeah, the beginning will be larger.
Yeah.
But given it's 10 landing, maybe you want us to do it.
But what kind of orbitals do you start?
You can start to use atomic light, but it's like you do
larger basis.
Yes. Larger basis, and the risk is over here issue. The 25 should be more, and the basis set should be more.
Yeah. No, no, we haven't tried it. So we tried with 6 nearest neighbors, and we actually managed to capture these pockets here in the band structure, which we completely missing with the third nearest neighbors.
So is there a reason why you want very few nearest neighbors accept basically because like a practical reason sort of really short range? You have 3 and not 4 or 5.
It's just because the Hamiltonian is sparser, and you can get away with the sparse matrices.
Okay. Thanks. Other questions?
Just one small technical one. What about the folding? Since you have this very big zones, then it's a problem of unfolding all the band structure, or
right. So that's a good question. So basically, what we do is we have this very large Moiré cell, which contains 1,000 atoms, and then we fold back states M and K, for example, onto the monolayer M and K. So there is a folding back onto the large states. But these, because of the geometry of the system, these are quite simple. So yeah.
Okay. I asked if there are questions online. Any other questions from you here? Okay. No, I said there are not. Okay, if there are no more questions, I think we should thank Valerio again.